Hello there, and welcome to my channel Engineering Progress, where we bring, dissect, and explain in easy-to-digest bits some of the most complex engineering feats and happenings. Today on this stream, we are discussing nuclear fission and fusion power for future space exploration. Also, please don't forget to click the subscribe button, destroy the like button, put on notifications, and drop comments below on this or any content you guys want to watch. Thanks! Space travel has been one of man's greatest dreams, having the ability to go beyond the comfort of Earth and travel to various galaxies and the great unknown for exploration in search of answers or just to have a nice time in the stars. But this dream has been hampered because we do not have the jet propulsion technology to properly escape our homeworld. But all these will soon be a thing of the past, as nuclear thermal propulsion, which uses heat energy from the nuclear reaction at its core for fuel, could be used one day in human spaceflight, possibly in the not-too-distant future for our colonization of Mars. Its development is the one true challenge, as the materials used must be able to withstand high heat and bombardment of highly charged particles regularly. There is a new space race developing, with higher stakes and more ambitious goals than just going back to Earth orbit or the Moon. The United States, which has developed a sizable lead on technologies in rocket and satellite technology, has in turn grown its national and global space ambitions. Now that it is practicable to get to low Earth orbit affordably and reliably, astronauts and private companies are now looking to take it further, including establishing permanent colonies on the Moon and Mars, mining asteroids for their immense natural deposits, and sending astronauts to search for life on the moons of the outer planets. And America is not the only one in this race. China and Russia are working together on a lunar base, and China claims it will be the first to colonize Mars and even mine asteroids. Nuclear fission and fusion power will be essential to accomplishing these and other ambitions. These technologies can deliver the performance, including immense power levels, longevity, and reliability, required to take large people and cargo astronomically long distances, and support the power requirements for long-term colonies far removed from the safety net of Earth. To this end, China is reportedly making investments in the advanced propulsion sector, including in fission and fusion contexts that dwarf U.S. effort. For the United States to remain competitive on the world scale and win what some are calling the new deep space race, they must double down on investment in nuclear fission and fusion technologies. Will Searight, a nuclear engineering doctoral student at Penn State, is contributing to research that could make these advancements more feasible. He published findings from a preliminary design simulation in Fusion Science and Technology, a publication of the American Nuclear Society. To better investigate nuclear thermal propulsion, Searight simulated a small-scale laboratory experiment known as a hydrogen test loop. The setup mimics a reactor's operation in space, where hydrogen travels through the core and propels the rocket at temperatures up to nearly 2,200 degrees Fahrenheit. Searight developed the simulation using dimensions from detailed drawings of tie tubes, the components that make up much of the test loop through which hydrogen flows. Industry partner Ultrasafe Nuclear Corporation, USNC, provided the drawings. Understanding how USNC's components behave in a hot hydrogen environment is crucial to bringing our rockets to space, Searight reasoned. We are thrilled to be working with one of the main reactor contractors for NASA's Space Nuclear Propulsion Project, which is seeking to produce a demonstration nuclear thermal propulsion engine within a decade. Advised by Lee Winfrey, Associate Professor and Undergraduate Program Chair of Nuclear Engineering, Searight used the ANSYS Fluent, a modeling software, to design a simulation loop from a stainless steel pipe with an outer diameter of about 2 inches. In the model, the loop connects to a hydrogen pump and circulates hot hydrogen through a test section adjacent to a heating element. Searight found that while consistent heating of hydrogen to 2,200 degrees Fahrenheit was attained, it was necessary to include a heating element directly above the test section to prevent a reduction in heating. Data collected from the modeling software showed that the flow of hydrogen through the test section was smooth and uniform, reducing the uneven distribution of heat through the loop that could jeopardize the setup's safety and lifespan. Analysis of the results also verified that stainless steel would allow for more convenient and cost-effective construction of the loop. The fusion rocket. So one might wonder, a fusion rocket? How's that possible? Are we onto some Star Trek imaginations right now? Well, a fusion rocket is a theoretical design for a rocket driven by fusion propulsion that could provide efficient and sustained acceleration in space without the need to carry a large fuel supply. The design requires fusion power technology beyond current capabilities and much larger and more complex rockets. Fusion nuclear pulse propulsion is one approach to using nuclear fusion energy to provide propulsion. Fusion's main advantage is its very high specific impulse, while its main disadvantage is the likely large mass of the reactor. A fusion rocket may produce less radiation than a fission rocket, reducing the shielding mass needed. The surest way of building a fusion rocket is to use hydrogen bombs as proposed in Project Orion, but such a spacecraft would be massive, and the Partial Nuclear Test Ban Treaty prohibits the use of such bombs. For that reason, bomb-based rockets would likely be limited to operating only in space. An alternative approach uses electrical, e.g. ion propulsion, with electric power generated by fusion instead of direct thrust. Spacecraft propulsion methods such as ion thrusters require electric power to run, but are highly efficient. In some cases, their thrust is limited by the amount of power that can be generated running on fusion power that could drive such a ship. One disadvantage is that conventional electricity production requires a low-temperature energy sink, which is difficult, i.e. heavy, in a spacecraft. Direct conversion of the kinetic energy of fusion products into electricity mitigates this problem. One attractive possibility is to direct the fusion exhaust out the back of the rocket to provide thrust without the intermediate production of electricity. This would be easier with some confinement schemes, example magnetic mirrors, than with others, example tokamaks. It is also more attractive for advanced fuels. Helium-3 propulsion would use the fusion of helium-3 atoms as a power source. Helium-3, an isotope of helium with 2 protons and 1 neutron, could be fused with deuterium in a reactor. The resulting energy release could expel propellant out the back of the spacecraft. Helium-3 is proposed as a power source for spacecraft mainly because of its lunar abundance. Scientists estimate that 1 million tons of accessible helium-3 are present on the Moon. Only 20% of the power produced by the DT reaction could be used this way, while the other 80% is released as neutrons, which, because they cannot be directed by magnetic fields or solid walls, would be difficult to direct towards thrust. Helium-3 is produced through the beta decay of tritium, which can be produced from deuterium, lithium, or boron. Even if a self-sustaining fusion reaction cannot be produced, it might be possible to use fusion to boost the efficiency of another propulsion system, such as a Vasmir engine. So, this poses the question, what are the confinement alternatives? Magnetic. To sustain a fusion reaction, the plasma must be confined. The most widely studied configuration for terrestrial fusion is the tokamak, a form of magnetic confinement fusion. Currently, tokamaks weigh a great deal, so the thrust-to-weight ratio would seem unacceptable. NASA's Glenn Research Center proposed a small aspect ratio spherical torus reactor for its Discovery 2 could deliver a crude 172,000 kilogram payload to Jupiter in 118 days, or 212 days to Saturn, using 861 metric tons of hydrogen propellant plus 11 metric tons of helium-3 deuterium DHE3 fusion fuel. The hydrogen is heated by the fusion plasma debris to increase thrust at a cost of reduced exhaust velocity, 348 to 463 km per second, and hence increased propellant mass. Inertial. The main alternative to magnetic confinement is inertial confinement fusion, ICF, such as that proposed by Project Daedalus. A small pellet of fusion fuel with a diameter of a couple of millimeters would be ignited by an electron beam or a laser. To produce direct thrust, a magnetic field forms the pusher plate. In principle, the helium-3 deuterium reaction or an aneutronic fusion reaction could be used to maximize the energy in charged particles and to minimize radiation, but it is highly questionable whether using these reactions is technically feasible. Both the detailed design studies in the 1970s, the Orion Drive and Project Daedalus used inertial confinement. In the 1980s, Lawrence Livermore National Laboratory and NASA studied an ICF-powered Vehicle for Interplanetary Transport Applications, or VISTA. The conical VISTA spacecraft could deliver a 100-ton payload to Mars orbit and return to Earth in 130 days, or to Jupiter orbit and back in 403 days. 41 tons of deuterium, tritium, DT fusion fuel would be required, plus 4,124 tons of hydrogen expellant. The exhaust velocity would be 157 kilometers per second. Magnetized target. Magnetized target fusion, or MTF, is a relatively new approach that combines the best features of the more widely studied magnetic confinement fusion, i.e., good energy confinement, and inertial confinement fusion, i.e., efficient compression heating and wall-free containment of the fusing plasma approaches. Like the magnetic approach, the fusion fuel is confined at low density by magnetic fields while it is heated into a plasma. But, like the inertial confinement approach, fusion is initiated by rapidly squeezing the target to dramatically increase fuel density and thus temperatures. MTF uses plasma guns, i.e., electromagnetic acceleration techniques, instead of powerful lasers, leading to low-cost and weight-compact reactors. The NASA MSFC Human Outer Planets Exploration, or HOPE group, has investigated a crewed MTF propulsion spacecraft capable of delivering a 163,933 kilogram payload to Jupiter's moon Callisto, 106 to 165 metric tons of propellant, hydrogen plus DT or DHE3 fusion fuel in 249 to 330 days. This design would thus be considerably smaller and more fuel efficient due to its higher exhaust velocity, 700 kilometers per second, than the previously mentioned Discovery 2 Vista concepts. Inertial electrostatic. Another popular confinement concept for fusion rockets is inertial electrostatic confinement, or IEC, such as in the Farnsworth-Hirsch fusor or the Polywell variation under development by Energy Matter Conversion Corporation, or EMC2. The University of Illinois has defined a 500-ton Fusion Ship 2 concept capable of delivering a 100,000 kilogram crewed payload to Jupiter's moon Europa in 210 days. Fusion Ship 2 utilizes ion rocket thrusters, 343 kilometers per second exhaust velocity, powered by 10 DHE3 IEC fusion reactors. The concept would need 300 tons of argon propellant for a one-year round trip to the Jupiter system. Robert Bussard published a series of technical articles discussing its application to spaceflight throughout the 1990s. His work was popularized by an article in the Analog Science Fiction and Fact publication where Tom Ligon described how the fusor would make for a highly effective fusion rocket. With that, we have come to the end of the video. If you enjoyed it, why don't you tell us what you think about the shortage of microchips and the future possibilities of nuclear power being used for spaceflight? Let's all hear your views in the comment section. Please share and comment on our amazing videos. Also, don't forget to like and subscribe to our channel to notify a new video like this is out immediately. Have a great day, guys. See you next time.